So it's my pleasure to introduce the colloquium speaker today, Jesus de Loera. He's a professor at the University of California in Davis. Jesus and I went to the same graduate school. He graduated from Cornell in applied mathematics in 1995, and he was a postdoc in Minnesota and in Zurich after that. And after that, he already got his job at Davis. Jesus is a fellow of the AMS, and he had many awards, including, for example, the Inform Society Award of 2010. He's an editor of several journals, including the Science Journal of Discrete Math and the Science Journal of Applied Algebra and Geometry. Jesus authored 2 books and more than 75 papers. And today we will talk about 100 years of Helly's theorem.
So it's a real pleasure to be here. I know so many people here in Raleigh that it's nice to put the faces to the names. And today I want to tell you a little bit of a nice story in convex geometry. So this is a very beautiful theorem that is today, I think this year is 100 years old. Oops. Let's try again. Something happened. Well, I'll just do it with my finger, I guess. So this is a little bit of introduction for. Oh, did I? Okay. So it's okay. I can do it with my finger. It's really on the side. Thank you so much. So, okay, convex geometry, just so in case you have never heard about it, very quickly. Convex sets are special subsets of R to the D, Euclidean space, where you have the property that if you have 2 points, and you consider the line segment connecting those 2 points, the line segment is always contained fully inside the set. So for example, we see here, this banana shape is not a convex set, because there's 2 points that the line is completely outside. But all the other objects, I mean, if I fill in the objects, the objects have to be filling in the interior, then they will be convex. So, well, this is not a convex set, as you can see, but these 2 are in the middle are convex. Yes, so, oops, I'm going in the wrong direction. There you are. So convex geometry appears everywhere, and you are familiar with many objects that are convex. And even, I mean, I will argue, okay, here are some more convex sets, and even some things are not convex in life, but the good news is that you can always find the smallest convex set that contains it. So for example, here I have a map of a country. So can anybody guess what country is that? Cuba. It's the map of Austria. Well, an approximation to the map of Austria.
This doesn't look like Austria at all.
It's my best try. Okay. So this map of Austria is not convex, as everybody knows. But nevertheless, there's a smallest convex set that contains Austria. Similarly, this girl is not convex, but there's a smallest convex set that contains the girl. So in general, that's one of the reasons why for many applied mathematics reasons, in optimization, for example, convex optimization problems approximate nonlinear optimization problems, and that's a good reason to study convex geometry. Now, what's the most famous example of a convex set? My favorite, and it should be your favorite example of a convex set, is a half space. So I take a plane in RD, and that plane breaks the space into 2 pieces. And each piece is a convex set. Now, a half space can be described by a linear inequality. So I have a very linear expression less than or equal than some constant. And that's fundamental because, oops, again I'm going to wrong. There it is. There's a beautiful theorem that you teach in every class in convex geometry that says convex sets are precisely the intersections of half spaces. For example, this blue convex set that you see here is the intersection of all the half spaces in the plane. So that for every line tangent to the convex body, you get some half space. And in fact, this is always true. So when you have a convex body, you can represent it as an intersection of half spaces. So people, the study of convex geometry is exactly the study of linear inequalities. But it's possible that you're going to study infinitely many linear inequalities. There might not be other choice. Like in this case, you need infinitely many linear inequalities. But for that reason, my favorite object in life, oops, again, I'm going to, there it is. These are my favorite objects in life. These are special convex sets because there's finitely many half spaces that you need to describe them. And these are the half spaces that define a convex polytope. So convex polytopes play a very important role in the theory of convex geometry because you can approximate any convex sets with convex polytopes. All right, so now that you are an expert, I gave you a class in convex geometry. Let's go to my favorite theorem in convex geometry, is the Theorem of Helly. So let's start by introducing the man himself. So if you want to know more about the life of Helly, I recommend you talk to Eric Kaltoff. So he will tell you a lot about it. Okay, so now let's talk about the theorem. 1914, according with what I learned. So this theorem says the following. Imagine you have a family of convex sets. I'm going to assume from now on that all my convex sets are bounded. They are compact, close, nice rounded things if you want, like, or polytopes if you wish. Okay, and you tell me that these convex sets live in d dimensions. And somehow you know that every time you take d plus one of them, they intersect. Then the theorem says that all of them have to intersect. So for example, here I have a family of 4 convex sets in the plane, and I check that every 3 of them have a nonempty intersection. Then the conclusion is that all of them must intersect. That's the most important theorem of today's talk. There is a magic number called n plus 1 or the dimension plus 1, which guarantees to you that if you have a system of convex sets and every time they intersect that many, then all of them must intersect. Let me rephrase the same theory in a different way. Suppose I give you a family of convex sets and you tell me, guess what, Jesus? There's no intersection of these convex sets. Then I can turn around and tell you, aha, there's a subfamily of your family that doesn't have intersection either, and it's only d plus 1 sets. Are you with me? Okay, so that's Helly's theorem. Now, you might be saying, well, is this a property of convex sets or what? So the first thing is that you need to observe that you really, really need convex sets. Why? Because if you take non-convex sets, the theorem is false. For example, here, I'm drawing for you, so look at the circle, and I'm drawing over the circle some arcs of circle. Just on the perimeter of the circle. I mean, it's not the disk, I'm looking at the circle. Now these arcs of circle, as you can see, they intersect, they overlap 3 at a time, right? Like for example here, you see these 3 arcs of circle intersect, but all the arcs of circle do not intersect. So you need something like convexity to be true. If you're a topologist, I know there's at least one topologist in the audience, you can weaken this condition to have some nice, topological spaces, but for now let's stick to convexity. Okay, not only that, not only you need convexity, but the magic number dimension plus 1 is necessary, right? Because here I have, think of these 3 disks. The disk is the most beautiful example of a convex set maybe, or the most classical. And so these 3 disks have the property that 2 of them intersect, every pair of them intersects, but not all 3 of them intersect. Yeah, so I have shown you that convexity is necessary, and that not only that, you actually need exactly d plus 1. There's a magic number, and that's what we call, and we will call all the time, this magically particular number will be the Helly number. Oh, again, sorry. Now, the story, so if you ever want to prove Helly's theorem, when I teach a class in convex geometry and I want to prove Helly's theorem, the most famous proof that is available in 99% of books is the proof by Radon. So Radon proved this, as I understand, after Helly did it, but nobody knew that. There was confusion on who was the author of this theorem. But Radon's proof is very elegant, and it uses a lemma that I will just tell you that is super easy to prove. I can give this exercise to undergraduates in linear algebra, because this is a result of just the ranks of matrices, okay? It's just a rank statement. But it says the following. Suppose you have D plus 2 points in RD. D plus 2 points in RD. Well, then there must be a way to label the points positive and negative, green and yellow, Republican and Democrat. You know, you label the points somehow, and then the partition of these points, you take the convex holes. That means the convex hole, by the way, is the smallest convex set that contains the points, and they will always intersect. Okay? So that's, here you see, for example, if I have 4 points, I can label them green this way and red this way, and they will have, a convex hole. Now, using this lemma and induction, you can prove Helly's theorem. So I'm just going to give you that hint, give it as an exercise to come up with the proof that Radon invented of Helly's theorem. It's very beautiful. Are you with me so far? Any questions, reactions, comments, complaints? No? Okay. Okay, now, I want to convince you that Helly's theorem is not just kind of, oh, that's kind of interesting. It's actually it appears in many different fashions that actually have very interesting applications. I will claim that it's a theorem in convex geometry and convex analysis that has utilities in other areas. So I will try to convince you of that today. So let's start with my favorite application. We are right now in North Carolina. Right? Am I right? Yes, we're in North Carolina, and you can even see Raleigh someplace there. Yeah, there's Raleigh. So the theorem of Helly implies the following remarkable fact. You pick a map of North Carolina, say this one. There has to be a point that no matter what line you let pass through that point, it will leave a third of the area of North Carolina in one side of the line. So that's the statement. Let me repeat it to you. So you have a point in North Carolina, so that any line that divides the map of North Carolina passing through that point will leave a third of the area on one side, for sure. And you can prove this using Helly's theorem. I'm going to give you a hint of how to do that. The idea of the proof is very simple. First of all, you put North Carolina in a ball. So you put it in a ball. And now you consider all the hyperplanes, or the lines that pass through North Carolina that leave at least 2/3 of the area of North Carolina in one side. Now this is a family of convex sets when you intersect it with the ball that contains North Carolina. And you can prove very easily that this has to have a Helly intersection, because it will satisfy the properties of Helly. So that point where they all intersect is the point where you should put the map. It's a point in the map of North Carolina where you will have them. So that's a beautiful application. By the way, it generalizes to dimension D. So you have an orange, there's a point in the orange that no matter how you cut it, there's at least a third of the volume of or anything that is convex. Alright? Okay, here is another Helly theorem. I mean, we're in the fashionable area of data mining. So suppose you have a set of data points for which you would like to find maybe clusterings of the points. You would like to find a circle or a ball that contains these points, and it has the smallest possible radius. That's your challenge. Well, Helly's theorem can be used to prove the following lemma, the following interesting lemma, that says, suppose you have a set of points, and every d plus 1 of these points happens to be inside a ball or a disc or something of radius r. Yeah? Then you can conclude that if this happens for every d plus 1 points, when you are in d dimensions, then you will have a circle of radius r that contains all of them, or a ball of radius r that contains all of them. So again, for example, if you have you're in the plane, and every 3 points contain, every 3 points are contained inside a disk of radius 1, then all the points must be contained in a disk of radius 1. And again, this is an application of Helly's theorem, because you can think of these convex sets intersecting sufficiently many times, then all of them must intersect. So this is a fascinating computational question. How can I actually find the smallest ball? So there are some people have worked on this quite a bit. For example, there's a very famous theorem of Young that guarantees that if you have a set of points, that the largest distance between a pair of points is L, so that's the diameter of the points. The farthest two apart are at distance L, then you can guarantee that there's for sure a ball of radius, square root of d over 2d plus 2 times L, covering the entire set of points. And there's a very interesting problem. This is actually, if you are familiar with convex optimization, I know you do, so you can find actually algorithms to find the use head. Oh, sorry. Go back. So you can find an algorithm to find the smallest enclosing ball by using Helly's theorem. So these algorithms are very popular these days in computational geometry, where you have the remarkable property of these algorithms is that it will depend linearly on the number of constraints. It will depend linearly in the number of points. And I will talk a little bit more about that. These algorithms require sampling points in sizes that are related to Helly's number. All right. Yes? Question? Okay, here is a different thing. So maybe this is more appropriate to the political climate we live in. So there's blue points and red points. Blue people, red people. And the question is, can I find a hyperplane that separates these two sets of people? Well, we know that this is not always possible. For example, here, you can see this is impossible to find a line that passes through these points and, divides the points into red and blue points. Yeah, you see that? So, but Helly's theorem has an answer for you for when you can actually guarantee a separation. So there's a version of Helly's theorem, it's called Kirchberger's theorem. It says that if you have points in Rd, and every time you take d plus 2 of them, and you can separate d plus 2 of them into the red points and the blue points, then you can always separate the blues and the reds. How do you like that? So all you have to do, if you want to separate the blue people from the red people, well, check whether every d plus 2 of these people can be separated. Right? So that's kind of the principle of separating people. It's based on Helly's theorem. We don't want that, right? We want the principle of integrating people, but that's a different story. All right. Are there any questions? So this is, again, it's almost a direct application of Helly's theorem. Here is one more application before I move to Helly's theorem in different versions. So here is an interesting one. So you have a set of points. For example, maybe you're doing computer graphics, and you have a bunch of objects. These are objects in a space, and you are wondering whether there is a line that pierces through them. Yeah? For example, maybe you want to shoot a bullet. I'm very violent today. You want to shoot a bullet through some objects, and you want to hit all of them with the same bullet. So the question is, when can I do that? And so Helly's theorem has one version that is kind of like this. So suppose you have intervals in the plane, and every time you have intervals in the plane, you can shoot an arrow, you can shoot a bullet through them, through any d plus 1 of them. Yes, I think, no, 3 of them. You just need 3 in the plane. Then you can actually find a line that passes through all of them. So remember, this has to be true like in Helly's theorem. Every time you take a triple of slice segments, you shoot a line and you pass through them, then you will find a line that passes through all of them. It's just a special case of Helly's theorem. How can you see that? Well, because if my objects are convex, I can project them into the plane that is perpendicular to my line, and I can see that this is a manifestation of Helly's theorem, right? You see? This is essentially asking about intersections of convex sets. Is everybody with me? Are you convinced now that Helly's theorem is a very, very cool theorem? All right. Okay, now, I don't know if you are like me, but if I like a car, like a red Ferrari, I want to have one like that. So, and I'm not the only one, I think, because a lot of people saw this theorem, and they start proving theorems that are like Helly's theorem. So I want to show you today a lot of theorems that have the same type of shape as Helly's theorem. So in other words, these are theorems that have some family of objects, polynomials maybe, or distributions, or something that you like, your favorite objects. What are your favorite objects? Whatever the favorite objects are. And then there's a property, maybe, they intersect, the polynomials intersect, or they have some property. And then there's a magic number that every time you take subfamilies of that size, something nice will happen. The property P will happen, then all of them will have that property. Are you with me? Yes, so you will never forget Helly's theorem now. Okay, first of all, Helly's theorem, the way I announced it, it was essentially for a finite family, and it doesn't have to be that way. So you actually can assume that there's an infinite family of convex sets, but they have to be compact. In this case, to prove that this is true, you need to have them to be compact. Now, here is one of my favorite versions of Helly's theorem, because this is going to be the first time ever you're going to see a different magic number. It's not going to be d plus 1 like before. It's going to be a different magic number. So you want to have a fat intersection. You want the convex sets to intersect on something that is fat. So how do you measure fatness of sets? By the volume. So imagine that you have a family of convex sets, at least 2D of them. You need at least 2D of them, where D is the dimension. And every time you take 2D of them, they intersect. But they intersect on volume at least 1. So not only they intersect, but they intersect in a lot of points with a large volume. Okay? Then, ta-da! Here's the conclusion. Then all of the members intersect on something that has volume at least 1 over 2 over D, 2 to the D. So if all the sets, every time you take 2D of them, they intersect on positive volume, all of them will intersect with positive volume. That's remarkable.
And
But
it
yes?
doesn't depend on n at all.
Actually no, it doesn't. So you can guarantee at least this number. If you have, okay, so there's several comments to this. This is the best that can happen in general. But in some cases it's better, right? I mean, you will see more volume happening, but there are examples for which this will be the best possible guarantee. Not you might say, I want more volume, I want more volume. Then you need to increase the Helly number. You need to let not only that all of the 2D of them intersect in something of volume 1, but you want more of them intersect on something of volume 1, then your constant will improve. That's a very good question. Let's work on that. Are you with me? Are there any questions? Okay. Here's one that I dedicate to all the friends in the audience that like polynomials, because this is actually what I call the polynomial Helly theorem. So you have a family of homogeneous polynomials of degree fi's of degree di. So let's call little, sorry that I changed dimension for degree. I apologize for that terrible sin. But little d is the maximal of the di's. Okay, so now, suppose you have this family of polynomials, they have no reason whatsoever to intersect, right? Or to have a solution in common. But, you promised me that this many of them, so let's call n plus d choose d, the magic number, this is going to be the magic number. Then, you tell me that every time I take these many polynomials, they intersect. There's a common solution of this system of polynomials. Then, the entire system must have a solution in common. Here's an example. if you have in the plane, you have curves. So these are two variable polynomials. You have curves of degree d. Then, and every time you do that, you take d plus 2 choose 2 of these curves. They have a real point of intersection that all of them must intersect in a real point. So in other words, if you have a billion parabolas or a billion quadratic polynomials, billion quadrics, but every time you check, there's 6 of them that intersect. Every six of them intersect, then all of them must intersect. This is a remarkable fact, in my opinion. Another way that you can think about this, for those of you like me that love the Hilbert-Nusselt sets, like you, I know you like it. So, if you have a system of polynomials that is inconsistent, there's a Hilbert-Nusselt set certificate that is of this size. So it's related to the minimal certificate size or sparsity of certificates as well. So yes?
How come that the convexity does not ruin your property?
Well, in some sense, the truth is that many of these theorems are, oops, sorry. I always go back. So, oops, no. Here. So, if you think about it, this is really a vector space embedding all the polynomials. So I'm kind of cheating actually here because this is related to the dimension of the vector space. So this plus one. So this is related to the vector space dimension. So all of what I'm saying here is really related to the fact that polynomial rings have a vector space structure. Now, what is really cool actually is that this is not the best Helly number. This is not the best Helly number. For that, you have to study the Macaulay matrix. I mean, you have to study the matrices that come in algorithms that we like. So then you get better Helly numbers for polynomials. All right. So here is another one that is not the same magic number. By the way, the previous one didn't have the same magic number. The magic number was not d plus 1, dimension plus 1, but it's kind of close. But this one, the one that I'm presenting now, it has a different Helly number. So you have now a family of convex sets that you know that every time you take this many of them, I know it's a funky number, it's the maximum between d plus 1 and 2d minus k plus 1. So d and k are given to you. D is the dimension, k is a magic k, some k. Then you take that many sets, they intersect on something of dimension k, then all of the sets intersect on a space that has dimension k. So this is a Helly theorem that guarantees that the intersection is fat, but it's not fat in the sense of volume. It's fat in the sense of dimension. Okay? Now I have so many versions of it. We can spend the whole afternoon here, but I don't want to do that. Here's one that I really like. Fractional Helly theorem. You have to know this one. I mean, you really have to. So I'm going to tell it to you. So remember, Helly's theorem is true if you take every subset of d plus 1 objects, something is true, then all of the sets are true. But maybe you don't have a perfect world. Maybe only a fraction, maybe only a fraction alpha of the possible. So there's n choose d plus 1 subsets, right? But not all of them intersect. When you look at these families, not all of them intersect. But maybe 50% of them intersect. 80% of them intersect. Can you get a discount? Can you get a discount? And the answer is yes. If you have an alpha or proportion of the total number of d plus 1 sets that intersects, then there's a proportion beta of the total that intersects. This is a remarkable theorem. I think this is really super cool. Really super cool. Because it's like Helly's theorem, but it's Helly's theorem with a discount, right? If 50% works, well, 30% of the total will work. Yeah, that's why I like it. It's called fractional Helly theorem. Now, here is another Helly theorem that is for boxes. And I have I'm going to leave you with a curiosity. It's a joke, but This has to do with politics as well. So the convex sets are boxes. The convex sets are, real rectangular boxes. And so they're not general, they're not general convex sets, too much energy. They're not general convex sets, but they're just access parallel boxes. Now, you tell me that every time, every time you have 2D of them, they intersect. But not only they intersect on a point, but they intersect on exactly the set of points S. So there's a finite set of point S where they intersect. Then, all of them must intersect on one of these special points. So you start with the special points, and then all of them must intersect. So this is the box only a Helly theorem. And this is special. This is special for two reasons, right? Because I use 2D as the magic number, and the sets are intersecting on a special chosen points. Now, can I write in the middle?
Oh no.
No, I cannot, right? I was almost gonna do it without asking you. But I realized that if I do that, I'll be having to pay $10,000.
No, we can write on that.
But
Not with a regular marker.
No,
that's what I meant.
With those markers.
Oh,
we
with the
can.
magic, these ones?
Yeah. Wait.
Yeah, those are the magic,
Yeah.
but then you have to tell me.
Oh, don't worry
Yeah.
then.
No, even the other ones. The other ones are.
It's not worth it.
erased-
I tell you what,
erased
at the end, remind me to explain you a political explanation of this term. I'm thinking about politics, obviously. Okay. Yeah, okay, so, are there any questions right now? In the last 20 minutes or so of this talk, I want to tell you my favorite Helly theorem, the one that I proved. Yeah, so as I told you, if you see a nice car passing in the street, you want to have that kind of car, right? So, is anybody ready? Okay? So my favorite kind of Helly theorem has to do with lattice points, discrete versions of Helly's theorem. So, first of all, lattice points in convex sets, I'm interested in points inside convex sets that have integer coordinates. So I'm working in the integer lattice points. And this is a classical subject that intersects convex geometry with number theory. So this gentleman is Hermann Minkowski, and he was the first, as far as I know, the first person, well, maybe Gauss also, but anyway, so this guy put the name geometry of numbers to the subject of studying convex sets and lattice points inside convex sets. And you can ask all kinds of questions. For example, you can ask, if I give you a convex set, is there a lattice point inside? Sometimes there are none, right? Sometimes you have no lattice points in the interior of a convex set. Or if you are like me, you sometimes would like to find the convex point, the lattice point in the convex set that minimizes or maximizes some function. So that's a possibility too. Maybe you want to count how many lattice points are there. That's a topic that is interesting for people in many areas of mathematics. Number theory for sure, representation theory, and so on. Or you want to generate a random lattice point. How will you do that? So these are questions that are very interesting. And I will show you today a theorem by Jean-Paul Doignon, who is giving you something about existence of intersections. It's a Helly theorem. It's a Helly theorem that guarantees to you that the lattice point, the convex sets will intersect on lattice points. So let me tell it to you. So you have a family, as usual, a family of convex sets in RD, but this time you promise me that 2 to the d of them, every time you take 2 to the d of them, they intersect, but they intersect on a lattice point. There's one lattice point for sure in the intersection of these convex sets. Then the conclusion is all the convex sets intersect in at least one lattice point. That's Jean-Paul Dougnon's theorem. So I'm phrasing it in the slides slightly differently. It's a very good way to think about this theorem. So you have a family of convex sets, and there's not a single lattice point in the intersection of them. Then I can tell you, don't worry, there's a finite family of 2 to the d of them that does not have an intersection either. That doesn't have a lattice point inside. Yeah? Are you with me? So that theorem was proved in 1973 And unfortunately, nobody read it. Well, at least two famous people didn't read it. So these are David Bell and Herbert Scarf. They are very famous economists. So Herbert Scarf unfortunately died this year. And he was nominated so many times to the Nobel Prize in Economics. David Bell is a professor at Harvard. Anyway, these guys are economists. And they were interested on Helly's theorem. Why do you think they were interested in Helly's theorem? Because, as I explained to you, you can think of Helly's theorem as about the existence of solutions of systems of convex equations with certain coefficients, right? In this case, they were interested in finding, they were interested in finding the integer solutions of convex constraints. Yeah? Convex optimization problems over the integers, essentially. So what they prove is the following. Let me rephrase it for people that like optimization. I know at least a couple of people like optimization in the room. So if you have a convex optimization problem that doesn't have an integer solution, well, there must be a subsystem that doesn't have an integer solution of size no more than 2 to the number of variables. So Doignon proved this in 1973, and I think 5 years later, these other guys proved it. It's 1977, they proved it. They didn't know of each other. Now, I call this theorem the Doignon, well, we call it the Doignon-Bell-Scarf theorem, some people call it, but it should be really Doignon's theorem.
Yeah, I think so.
It should be really Doignon's theorem. Anyway, so I just want to say, there's a very sleek proof of this theorem, but I'd rather finish the presentation to show you the proof you want. But here's my theorem, or here's our theorem. This is joint work with Iskander Aliev, who's at the University of Cardiff in Britain, in Wales to be more precise. Edouard Louveaux, who's at Université Liège in Belgium. So we prove a counting lattice points theorem for convex sets. So again, you have a family of convex sets. And there's a magic number. So I'm going to tell you what the magic number is in a moment, but there's a magic number that depends on D and K. This that I mentioned, K is the number of lattice points. Not just one lattice points, but K lattice points. And every time you take these many, every time you take CDK many convex sets, they intersect, and inside the intersection there's K lattice points. You promised me that. There's exactly K lattice points in the interior. Then, all of them must intersect and inside there's K lattice points. The constant that we can prove, so the magic constant CDK is bounded above by this number. So it's a generalization of Doignon's theorem. So the generalization of Doignon's theorem because, for K equals 0, when you don't have lattice points, essentially, you can get back Doignon. But this is counting how many lattice points you guarantee in the intersection. It's like the volume theorem that I showed you before, where you're measuring how fat the intersection is, but this time it's a discrete measuring of fat. Yeah, discretely measuring fat. So you have to take these many sets, and then you can guarantee that there's enough intersection. So you can use this to do other things. So how about the magic number? So this magic number, I know is exact for K equals 0, because we know it's tight for Doignon. We prove that it's tight for K equals 1 as well, when you want to guarantee that there is exactly one lattice point in the interior. But we know it's not tight for K equals 2. So, for the young people in the audience, we need young people to work on this. So, please find the exact constant for K equals 2. I know that this constant is not the right constant for K equals 2. It's the first case that we know is not true, and that is not tight. Well, young people at heart, so your age doesn't matter. I'm talking about your spirit. You can work too, people that...
Yeah, but when I do it, you ask me for K equals 3.
Oh, well, I'd be happy if you can get K equals 2. Yeah, so by the way, so here is the open problem again. By the way, these are the best configurations. For K equals 1, the values are 6. If you want to guarantee one lattice point in the plane, you have 6 convex sets, you will have for sure, this is the magic number is 6. And for dimension 3, and you want to guarantee that there's one lattice point, will be 14. 14 is the size of the sample. Yeah, so counting lattice points, I think I mentioned it already, but anyway, so it's applicable in representation theory, commutative algebra, combinatorics. This is one that I wanted to mention. For example, you would like to count lattice points on magic squares, or maybe you want to count Sudoku. I was going to mention Sudoku. So there's a very cool problem. So you know Sudoku, right? Everybody knows Sudoku. You have this puzzle with numbers. You're supposed to put the numbers 1 through n everywhere, 1 through 9. But you give me some clues. You give me only some clues, and I'm supposed to fill the rest. But here's a question. What is the smallest number of hints you need to fill the square in such a way that there's a unique solution? It's related to the question that I'm telling you, right? When you want to guarantee that a system of equations has exactly one solution, what conditions do you have to put to have that? Here's one that maybe Eric will like. Let me just mention it. So, counting lattice points in general convex bodies is a mess. Because, for example, if you could count lattice points on a 4-dimensional ball, then you can break RSA. There's a number theoretic trick you can perform, and then you can, if you know how to, for instance, if you know how to count lattice points of 4-dimensional balls, then you can factor integer numbers of the form p times q, where p and q are prime. And this is shows you that counting lattice points in general is a nasty business, even in convex sets. Even in convex sets. Okay, so I come to the end of my lecture. The last part of my lecture. I have about 10 minutes. Okay, so I want to talk a little bit about algorithms and Helly's theorem. So the first thing. So there are a number of questions that you can ask about convex sets. So how can I find a point that is in the intersection of these convex sets? That will be one of them. Or, for example, I have a list of problems here. So for example, you want to solve linear programs, integer linear programming, convex optimization problems. You may actually be interested in finding also the problem that I mentioned before. You have a set of points in RD, and you want to find the smallest radius ball that contains these points. And, or you want to, for example, find the separating hyperplane, so that gives you a set of points. So all these problems have something in common. They have Helly's theorem in common, right? They have Helly's theorem in common. And I forgot one important example. There's one more. Of course, is the problem. You have a set of polynomials for which you want to find the roots. You want to find a root, and you want to find a subset that has the same set of roots. You want to find a subset of the algebraic variety that has exactly the same set of roots. So all these problems have in common Helly's theorem. Now, imagine that I have a billion constraints. So in other words, I have a billion polynomials. I have a billion polynomials, or I have a billion convex sets, so you cannot even read them in memory. You cannot even read these problems in memory. Okay? So, for example, if I have a billion points, I cannot expect to read them in my computer, but I know that only 3 of them, in the plane, only 3 of them define a circle. Right? So, here is something that looks very stupid to say, but it's actually very elegant. So, the more you sample, you sample points, you say you can only sample 3 points at a time. Let's talk about this problem. The problem of finding the smallest enclosing circle. So you sample 3 points at a time, and you can find a circle that contains them. If all of the points are inside, then you make a party, you're done. But maybe some points are outside. So you sample again, but this time you try to sample in a clever way that makes the points that were outside the original circle more likely to appear in the next sampling. So there's a sampling methodology that was invented by Ken Clarkson that allows you to sample with more probability things that are violated. So you are more likely to sample things that contain all the points inside. Similarly, you are more likely to sample polynomials that have all the roots. Okay? And this procedure, the Clarkson algorithm, works as long as you have a Helly number. That's the miracle that I'm communicating to you. If you have a Helly number, which is the case in all these cases, in all these situations, then a miracle happens and you can sample just Helly number many constraints at a time. You sample and make this Clarkson algorithm sampling style, and you will arrive to, after I'll tell you the complexity, you will arrive to a solution that contains all the points, or a solution that is a solution of all the polynomials. Now, what's the complexity? The complexity is going to be linear in the number of constraints. So you only need essentially to test every polynomial once, or deal with a polynomial once, but the complexity will depend exponentially on the dimension. Will depend exponentially on the dimension and on the time that you need to solve the specific problem of just the sampling size. Now, when you are dealing in fixed dimension, when you are working with fixed numbers of variables, all these problems become actually polynomial time. It's a polynomial time algorithm, and it's in fact linear in the number of constraints. So that algorithm is the fastest algorithm we know to solve linear programs in theory, at least. So these are the Clarkson style algorithm, and if you have heard about linear programming, random edge, or random pivoting rules, this comes exactly from these kinds of algorithms. And it depends on sampling Helly size subsets. Alright, so I think this is the end of my speech. So let me just tell you that, so you should study convex geometry. It's good for you. It's low fat, fat free and all that. So, and it can be applied in many areas of mathematics. I forgot to put here symbolic computing, but it's also good for that. And anyway, so there's a ton of open questions. I can tell you, if you are still interested, young people want to hear some more open questions, like the one that I mentioned. I'm still around for a few more hours. Thank you so much.
Questions?
Yes. The fractional Helly theorem?
Yes, let's go back.
Can that be extended to some of the other Helly type theorems?
Yes, as a matter of fact, here's an amazing fact. If you have a Helly theorem, you have your favorite Helly theorem, there's always a fractional Helly theorem. That depends on n choose whatever your Helly number is. So you replace, instead of being n choose d plus 1, you replace with n choose your Helly number. For example, my favorite one, the one that I proved, has a fractional version, but then you need to look at a proportion of the families of size Helly, of the original Helly that you're working with. Yeah. Yes?
Can you go back to the map, the portion theorem?
You mean the boxes or which one?
You had the map of North Carolina.
The map of North Carolina, yes, absolutely.
So can you state this again?
Yeah. So there is a point that every line that passes through that point will leave at least a third of the area for sure in one of the sides.
But if I draw a line,
both
then
of
I
the
always
sides.
have
In
one.
both of the
One
sides.
third
Yes.
is not enough.
Yeah.
I know.
Yeah, in each side, sorry. At least a third of the area in each side. I really didn't say it correctly. Thank you very much. Yes. Yeah.
It doesn't matter that North Carolina is not convex.
It doesn't matter that it's not convex. It doesn't matter that
The
it's
1/3 number comes from.
But there's, I'm sorry. It doesn't always, because if it is a convex figure, then you can be sure that the point is inside the convex set. But because North Carolina is not convex, it might be outside North Carolina. It's just in the plane. Yeah.
And
So, yes.
the number 1/3 comes from the fact that it's a two-dimensional program, or
The proportion that you can guarantee is 1 over d plus 1. 1
So
over
the
the
orange would be.
In an orange, it will be at least 1/4 in one side, in each side of the plane cutting through. Yeah, and in general like that. Yeah.
Somebody.
Yes.
In your result or Doignon's results,
Yes.
if you assume that the convex sets are half spaces, then the hope of tightening goes up in times.
Can you repeat your
If the
question?
convex sets your half spaces.
Yeah. So the version that you can state it as. So this is, I think, one version that directly applies what you're asking. So you have. So there you have a collection of half spaces. So it's a linear, it's a polyhedron, right? You're given ax less than or equal to b, and you tell me that there's no integer solution of this system of inequalities. Then there's a subsystem of size 2 to the d that also does not have solution over the integers.
Did I miss your political joke about the box?
Oh no, you didn't miss it. You didn't miss it. But I need to raise this.
Okay, I can do that.
Well, it's not. I don't know if it is a joke. It's actually a serious. I'm very serious. I never joke. I never joke about mathematics.
Power up.
Okay. Okay. So yeah. So remember the Helly theorem for boxes says that you start by picking a special set of points. Okay, so these are candidates from some party. I'm not gonna say which one. You figure it out. You figure it out. So now you pick, and now you are the voters. You are the voters. You are boxes, because every voter. I'm gonna just draw a two-dimensional box here because, I cannot draw three-dimensional boxes very well, but you will really understand. So for example, my box is here. My box is here because these are my opinions on taxes and gun control. And that's the range where I am. But some people will be here. Yeah? Now, your political party wants to have somebody elected. Right? What does that mean? You want to guarantee that the set of all boxes contains one point that everybody likes. I mean, in the ideal situation. So if you have 2D boxes containing one candidate from this party, then you can guarantee that all the boxes will intersect on a candidate of that party. So in other words, if every 2D opinions capture there's one candidate that is captured by every 2D opinions, then all of the opinions are captured by somebody. So it's not quite a joke, but it's really a theorem. Now you might be saying, but that's not how you win elections, as we know. So how do you win elections?
You find the least covered.
Well, okay, there you are. So now what you do is you want a proportion, right? You just want a proportion of the candidates to be likable, or that sufficiently many like. So then you use fractional Helly's theorem. Then you use fractional Helly's theorem on this theorem, and then you get it. So it's not a joke, it's actually true. This is something that I saw some French political scientists thinking about, and we told them that they can use Helly's theorem. Yeah.
Any more questions?
Yes.
So you were giving everybody what they like, so I like quantitative theorems. So for let's say a bunch of convex sets, no common intersection. And then Helly says there is, of course, there are some p plus 1 subset of the intersects. So what about the generic case? How many you should, let's say, sample to check out there's no common intersection?
Well, I think that's related to the fractional Helly theorem, right? So, well, essentially your question, let me rephrase your question. So, I want to have a certain guarantee of intersection, say, at least 80% of them are sure to guarantee. What's the alpha proportion that I need to be sure to get that, right? And that actually is a very interesting question. This fractional Helly theorem, I mentioned alpha and beta, these are the two proportions that are involved. We don't know very well beta from alpha. So there's some open questions about figuring out exactly the proportions that are necessary to guarantee intersections. And this depends also on the type of Helly theorem you have.
Is this something new or long-standing of the problem?
Well,
Because in convex
You know,
geometry,
at my age, you think it's new. Yes, it's new. Very new. Very new. Yes. No, I mean, I think this has been around for at least 10 years or something like that.
Any more questions? Let's thank again for